Okay, so we're finally ready to finish the proof of this long series of equivalences, right? So let's see what we have here. Well, as before, K D sub K is our compact is our metric space, and we need a criterion to show that it's compact. And what do we have here? So we have a lot of things. So first of all is the topological definition of compactness, meaning open covers have finite subcovers. I'm not going to remind you exactly what that means because we're going to see in the proof. Okay, and we proved before, even in the topological setting, from this topological compactness property, we know that every continuous function over K must achieve the sup and the inf. Right? There are points at which the sup is achieved, the inf is achieved. And from this, you also argued that continuous function from K to R have to be bounded. Then came the harder stuff that we did in other videos. We showed that if all continuous functions from K to R are bounded, then the space must be complete and also totally bounded, right? Complete, we use this function that's the limit of the distance from x to x sub n, where x sub n is Cauchy. And to prove K is totally bounded, we showed if K is not totally bounded, we have an infinite delta packing for some delta, and we can build this 10th function, right, that gets taller and taller. Okay, so we know that 3 implies 4. We also know that 4 implies 5 that was shown in the previous video. Basically, I argued that if K is totally bounded, then all sequences in K have Cauchy subsequences. Then if K is complete and totally bounded, these Cauchy subsequences have to converge. And recall that's precisely what we mean by subsequentially compact, that all sequences have convergent subsequences. There's something else that we proved, which was that 5 implies 2. That we proved when we introduced this theorem. It's this classical argument that if K is subsequentially compact, then you can look at a sequence of points in K that nearly achieves the infimum of F. And by finding a convergent subsequence, you find a point, which is a limit of the subsequence, where the infimum is actually achieved. So both, and you can play the same trick with the sup and the inf. Okay, so what's our situation? Clearly, we know that 2 to 5 are equivalent. So by assuming any one of these, we know that the other must be true. What is missing is an arrow connecting these guys to 1. And that's what we're going to add to the diagram right now. Basically, what we're going to do is to say, okay, if you have a space that's totally bounded, where continuous functions achieve the sup and the inf, then every open cover must have a finite subcover. How do we do that? Okay, so I say K, but I should say K satisfies 2 and 4. So these are the two properties we're going to need to prove that every open cover has a finite subcover. Okay. So what does it mean? That these sets are open in the topology of K, which might be the relative topology if K contains a larger space, but the important thing is that K is the union of these guys. How do we find a finite subcover? So first of all, a simple observation. For all x in K, there exists a delta, and there exists a set A in the cover, such that Bx delta is contained in A. Why is this simple? Okay, take an element of K. It's contained in one of the sets A. Say that set is A sub x. Right? So if x belongs to A sub x and A sub x is open, there's some open bubble around x that's contained in A. And that's how you find the delta corresponding to x. Basically, the main thing we're going to do in the proof is to invert the quantifiers here. So my main claim in the proof is this. claim is that there exists a delta, so it's that for all x, sorry, I keep switching k and x in my notation. And for all x and k, there exists an open set in the cover. And of course, this delta now doesn't depend on x anymore. And it's not at all clear at first sight why this should be sufficient for the theorem to hold. But look, we have an additional property, right? So what we claim is that there's a delta that works for all x. So given x, if I take the ball of radius x of radius delta around x, there is a single set from the open cover that entirely covers this ball of radius delta around x. And why is this useful? Okay. Note that k, remember k is totally bounded, right? So k is covered by a finite union of open balls of radius delta, just because this works for any delta, right? So I'm assuming the claim, and I'm just saying, okay, if there exists a delta, no, I don't care what it is. What I know is that there's a finite number of balls of radius delta that covers this set. Okay, I mean, you might object because we usually use closed balls here, but we know, for instance, a case covered by a union of closed balls of radius delta over 2, the open balls contain those closed balls, so we're good to go. And okay, so, and why is it equal? Why is it not contained? Well, because in our setting, we are working with K as the whole metric space, so there's nothing outside of K. So saying that K is contained in this union means that K equals this union. Okay, big deal, so what? Notice that each ball like this, if our claim is correct, is contained in AX sub I, right? One set in the cover. So K is contained in the union from I equals 1 to K of AX sub I. And, well, it's actually equal, right? Because, again, nothing lies outside of K in our universe. So what did we do? We found a finite subcover. Again, what did we do, right? So we said, okay, the claim gives us a radius that can be covered for any x. If I take the ball of that radius around x, it can be covered by a single set in my open cover. Now, I know that finitely many balls of radius delta cover K just because it's totally bounded, right? So this is in item 4 here. So K is totally bounded. It's covered by finitely many balls of radius delta. Each one of these balls is contained in the set of the cover. But then the union of these sets covers the union of these balls, which is K. And therefore, these sets, this finite subcollection of script A, covers K. And we found a finite subcover. So, I mean, this claim, though it looks kind of weird, it's saying basically that something that in the end kind of makes more sense, as your proof progresses, that's going to make more sense, is this. So, I want to find for each x the largest radius so that I can guarantee that the ball around x of that radius is covered by a single set in my cover. And it turns out that this largest radius has a universal lower bound. There's a delta that's a lower bound for the largest radius for all x simultaneously. Okay, but how do we prove that? So, okay, hopefully this is clear. If the claim is true, then I can cover K by finitely many open balls of radius delta, or finitely many closed balls of radius delta over 2. Okay, each one of these balls is covered by one set in my open cover, and therefore finitely many open sets from my open cover they cover the whole space K. And we're done. So if the claim is true, everything follows. Though the claim might be seem hard to prove, right? So how do we find this radius, this largest radius? Well, in fact, that's precisely how we're going to define things. So I want to prove the claim now because the claim implies the theorem. How do we find delta? Okay, so let me For x and k, I define the set I of x as the set of all deltas that I defined before, say between 0 and 1. I'm just going to put an upper bound because, because I can't really. Okay, but I'm just going to say that delta is the set of all deltas such that there exists an a sub x in the cover such that the ball of radius delta around x is contained in a sub x. So for each k, I can define the set. The set is actually an interval. Well, it actually has the following property. So for all delta belonging to ik, the interval from 0 to delta is closed, is entirely contained in ix, because if I have a set in the cover for this value of delta, for any smaller value of delta, that same a sub x works, right? So if I take a smaller delta, you have a smaller ball. Okay, and now I said I want to try to find the largest radius, the largest delta for which I have this thing. So I'm taking R of x to be the supremum of the set I of x for x in k. So it's the largest possible radius that gets covered by a single ball, except I'm putting an upper bound of 1 here because I don't want to get an infinitely large radius. Even if I can, I don't want to do it. Okay, so why is this well defined? Well, this is a bounded set of real numbers, so it has a supremum, no big deal. Another important fact is that we know, right, we argued before that this set here contains non-zero elements. So, okay, actually 0 is not here, right, because we know that for all x are contained in some set of the cover, because k is covered by the open cover, so all x belong to one of these sets, and if I fix it, this set, it's open, therefore there exists a positive delta. So the sup is greater than 0. And we'll show that R is a function from k to 0, 1. That's one Lipschitz. So this is sort of a claim inside the claim. I claim that this function is one Lipschitz. What's the consequence of that? So if you accept that this function is one Lipschitz, is R of x, what is the consequence of that? So the consequence is that if it's one Lipschitz, you take the infimum, well, that's equal to R of x minus, right? Remember property 4. R is a continuous function, it's a one Lipschitz function, so it has to achieve its infimum. So by property 1, this infimum is achieved by some x minus belonging to k. But R is always positive, right? So the infimum has to be positive. And that's what we need. The infimum is positive. And then we prove the claim by taking any delta that's between 0 and the infimum. And you just have to check that this delta works. Well, why, right? If delta is less than the infimum, then it's easy, to, right? Because the set here does this interval structure, it's easy to see that I of x has to contain delta, right? So basically what I'm saying is that, okay, I of x has to be the open interval from 0 to R of x. Well, you have to check that, but it's true, right? So in the end, I have that I of x is the interval from 0 to R of x. And therefore, if I take delta here, this interval is contained in this one, and this delta, therefore, belongs to I of x for all x, and therefore, for all x, there exists an a sub x such that the ball of radius delta around x is contained in a sub x. And then we're done. So we need to show this thing. We need to prove that this very abstract function, or, I mean, it's not that abstract, right? But it associates with each x, or the largest possible radius around x that can be covered by a single element of my open cover. I need to show that this radius depends on the Lipschitz fraction on x. How do I prove that a function is one Lipschitz? It's a function from k to r. right? To k to 0, 1. Okay, what do I need to show? I want to argue that if I compute r at two different points, the difference in the values of rx and rx prime is at most the distance between these points. Okay? So that's what a one-Lipschitz function satisfies, except that we don't actually need to prove all of that. We just need to prove this without the absolute value. And I think that by now we know why that is, because if I have this for all x and x prime, I can reverse the roles and I have an inequality for r of x prime minus r of x, bounded by the same distance, because the distance is symmetric. And therefore I have an inequality for the absolute value, right? So how do I prove this? Okay. Okay, so I'm going to give a geometrical proof of this fact. I'm not going to write down this inequality here. Here's what I'm going to do. Take x, and this radius r of x, and we know that there's this ball around x that's entirely contained in the set A sub x, right? Now, okay, take x prime, and I'm going to assume that the distance between x and x prime is less than this radius here. It's just, I mean, on the picture, right? So, and this is, well, let me call this alpha. This is alpha. So notice that if alpha is greater than r of x, then this inequality is certainly true, right? Because r of x is less than alpha, r of x prime is positive, so this is less than r of x, right? So the interesting case is when this number is less than r of x. And maybe from the picture is already clear what I'm going to do. My claim is that if I take a ball slightly smaller of radius, kind of basically what I'm saying is this, so that if I take a ball of radius r of x minus alpha around x prime, that's still going to be contained in A sub x. So to repeat, I mean, my picture is not very good, and I'm going to explain why in a second. But my claim is that if I take this ball of radius r of x minus alpha around x prime, then this ball is entirely contained in the ball radius r of x around x, and therefore entirely contained in this set A sub x that belongs to my open cover. Okay, let's be a little bit more analytic, because so take a delta, any delta that's in I of x, which I've argued is an exercise for you, is precisely this interval from 0 to little r of x. And, well, at least it contains this interval. So I should have said it contains this interval, because it could be closed here as well. In principle, I guess. Yeah, it could be closed. That's right. Okay. So watch. It's, right, if I take a delta in this interval, then I know that bx delta is contained in A of x for some A of x belonging to the open cover, right? That's the definition of a set I of x. If I take delta in here, there's a set in the cover that covers the ball of radius delta around x. Now, look at the ball around x prime of radius delta minus this alpha here, the distance between the two. Okay, strictly speaking, this this doesn't make sense if this number is negative, right? So let's assume this number is positive. Well, in any case, this is a kind of argument that I have seen, right? So that I have the ball of radius delta around x. I have an x prime here. So the smaller ball of this radius delta minus the distance is contained in the ball of radius delta. I mean, does it look like it because I screw up the drawing, but it makes sense. So this is contained in b x delta, which is contained in a sub x belonging to the open cover. So now again, assuming delta minus the distance is positive, I've found a radius such that the ball of that radius around x prime is entirely covered by an element of my open cover, by none of the open sets in my open cover. By this argument, what I have proven is this, so that that this inequality is true, because that's the same thing as saying that delta minus the distance is less than or equal to r of x prime, right? So basically I'm saying this, the delta minus dk x prime belongs to I of x prime if this number is greater than 0. So, okay, and from this I want to say, well, if this number belongs to the set, then it's less than the supremum, well, which is r of x prime. And now delta is any number less than r of x, so by increasing delta, right, so, okay, sorry, before I said this, right, so that this thing here belongs to I of x prime, because this is if this is a positive number. And why is that? Because this is a positive number. And when I look at it, I can see that a ball of this radius around x prime is completely covered by an element of my open cover. Now, from this, I want to conclude that this is less than r of x prime. Why is that? Well, if the number is positive, it belongs to the set I of x prime, and it's got to be less than the supremum, right? If this number is negative or 0, then certainly this is true too, because this is positive, right? Remember that r of x is a positive number. There's one caveat to what I said, because it could be that this number is greater than 1, right? In which case we'd have trouble because we limit the set to 1. However, delta is an element of I of x, so therefore delta is less than 1 or equal to 1. And this guy here, well, delta minus this guy has to be less than 1 as well. So there's no caveat. So this holds, and it holds for a delta that belongs to I of x. So for any delta that's strictly less than the supremum, which is r of x. Right? So for any delta like this, I have this inequality, and then I can increase delta. If I take delta converging to r of x, this gives me the following inequality. And if I rearrange terms, that's like saying the difference of r of x minus r of x prime is less than the distance, which is what we wanted to prove, right? So we wanted to prove that r is a one Lipschitz function. So therefore, that r of x minus r of x prime is less than the distance between x and x prime for all x and x prime. So this disappeared. And this is how I do it, right? So r of x is the supremum of these delta. For any such delta, this guy here, if positive, belongs to the set I of x prime. Now, this guy, if it's positive, delta minus the distance is less than r of x prime, because r of x hides the supremum of the set I of x prime. But if this number is not positive, then this inequality holds regardless, because this guy is positive and this would be less or equal to 0. So we have this for any delta here, and we can increase delta to get this inequality, which is what we wanted to show. So to backtrack, we had this claim that a no implies a theorem by this argument that since K is covered by finitely many balls of radius delta, if I cover each one of these balls by a set in my open cover, right, an A of X in the open cover, then I can cover the whole space by finitely many sets from my open cover. So the interesting thing about this argument is that it says, here I have an arbitrary open cover, and when I find a finite subcover. So I know how to find finite coverings by balls of radius delta, and that's what I use here somehow. It's just going to make sure that I have the same delta all over the place. Okay, so the claim implies a theorem. How do we prove the claim? We find this delta by taking the sup of a continuous function, a continuous and positive function. Right, we define this I of X, a set of delta such that you can cover the ball of radius delta by a set in the open cover. We find these guys here. Then we have R of X to be the supremum. And we prove that this function R of X is positive and continuous. It's actually one Lipschitz. Since it's positive and continuous, it achieves its infimum. And its infimum must be then strictly positive, right? The function is positive, so the infimum has to be positive because the infimum is the value of the function somewhere. And now that we know the infimum is positive, I can take any delta that's strictly less than this infimum of R of X, and this delta works to prove the claim. And that's it. That's a pretty sophisticated proof, but it shows us the last remaining implication. 2 and 4 imply 1, and therefore all of these guys together imply 1. Remember, they already had shown them to be all equivalent. So now we know that all these items are equivalent to one another, and we're finished with this grand equivalence. That's it for now. Thanks.